All right, it's week 7, and we are going to talk about color today. So, the first rule of color is don't talk about color, or rather, don't just talk about color. We need to decompose it. It's incredibly confusing if we treat it as something that's monolithic. So, what we need to do is we need to decompose it into luminance and saturation and hue. So the reason we want to do it this way is that luminance, that is how bright something is, in luminance it varies from black to gray to white. So how bright something is, that's ordered. That's one of these ordered channels. It's a magnitude channel. And saturation, how colorful something is, that's also ordered, right? We can go from gray through sort of dusty pink to a more saturated, vibrant pink like we see here. So those are two ordered channels. But hue, like what color is something, that's an identity channel. That's good for categorical uh, data. So we can say, what color is it? Is it red? Is it blue? Is it purple? So what color as opposed to how bright or how saturated. And so that's this key idea that we're going to talk about at length today, is that we really need to consider the luminance and the saturation channels as magnitudes and the hue channel as an identity. And that can really dictate whether we're showing ordering or categorical in the data. And of course, as we know, because we've learned a lot about channels so far, these all have different properties of what they convey to the perceptual system. Um, and they're just like we did a lot of analysis with, tabular data and other data of what scale of data can we convey. We always have to think, how many bins, how many different understandable bins of color can we use? And we'll be talking about that today. So from the point of these channels, what are they conveying? How much information can they convey in terms of different levels of the attribute, different bins of the channel? So just to underscore this point about whether luminance and saturation and hue are ordered, unordered, right? If I gave you and a friend 4 paint chips and said, okay, there's a black and there's a light gray and there's a dark gray and there's a white. And I put you in one room and your friend in the other room without a phone so you can't communicate. Said, put these in order. Um, I'm going to bet that you always have this order where it goes, white, light gray, dark gray, and black. That's just it's an intrinsically perceptual order. Our eyes see that order. Maybe we'll go the other way, black to white or white to black, but gray is always going to be in between white and black. But in contrast, if I gave you and your friend 4 paint chips and it was purple and blue and red and green, and I did the same thing where I put you into 2 rooms and I said, put these in order, I would not bet $1,000,000 that you would put them in the same order. Does green go in between red and blue? Maybe not. Where does purple go? It's just not obvious. It's because it's not a perceptually ordered situation. Our eyes do not intrinsically place hues in order the way we place luminance in order, the way we place saturation in order with those top 2 rows. Okay, so um, reminding you to put this in the bigger picture of all the channels that we've talked about so far. We've talked a lot about position, both aligned and unaligned, and we've talked about length and area. But now is the time that we are talking about color, luminance, and saturation as magnitude channels and color hue as an identity channel. Sometimes I admit, just use the word color. Often when I just use the words color, I'm mostly talking about the categorical hue aspect to it. So, we will sometimes just say this is color coded. And typically what we mean by that is hue. And then if we really mean these magnitude channels, will often be more specific. All right. So let's make sure we fully understand what these are, this idea of hue and saturation and luminance. So let's talk about different ways to discuss color more theoretically and practically. So those of you who've done any sort of web development or computer graphics have probably dealt with RGB, that is red and green and blue, and you know that we can express any color that can be shown on a display as some combination of a red and a green and a blue channel. And here's a few different depictions of, and notice how you can actually think about this pretty easily. It forms a cube. We can have a cube where the corners of it are these fully saturated colors of yellow and green and cyan and magenta. And then we have these two other corners of white and black. And you can you can vary to get any color. But what's this not good for? This is not good for visual encoding, because if you just specify red and green and blue, you can't really easily separate out that color, the colored hue part from that luminance and saturation ordered data. So we can't do this whole categorical versus ordered data encoding very easily if all we're given is RGB. It's just really hard to think about encoding in that way. And it's also not very good for interpolating. Any of you who've tried this in a graphics class will know that if you just take some RGB color value, right, like 0.2, 0.8, 0.6, and then you try to interpolate just through RGB space to some other value, you might get some really surprising colors in between. So it's definitely not a perceptual space for interpolating. So, well, what else could we do? We've just talked about this idea of having a luminance and hue and saturation space, and that's really good for visually encoding. Unfortunately, since visualization has not taken over the world the way computer graphics has, there's not very many tools that actually let you directly work in this space. Um, Now, some of you who've done any sort of graphic design, like using something like, say, Adobe tools, might have noticed that there is a color space that sounds pretty similar. It's sometimes called hue, saturation, and lightness, or hue, saturation, and value. Um, and there's a lot of tools out there like color pickers where they give you this wheel of color, and notice how it's fully saturated. This is the fully saturated on the outside of the color wheel. So you can sort of go around the wheel to get to different hues. So this lets us really think about hue. And then as we go towards the center, we're going to desaturate. So we get more and more towards white. And then there's usually some sort of slider control for controlling the amount of darkness. Um, these are technically two different spaces. In both of them, they have this idea that there's the hue saturation wheel. Um, and one of them is a double cone where you go up towards white and down towards black. The other is a single cone where you have white in the middle of the wheel and then you just go down towards black. And so they capture some stuff. They capture this idea that it's really helpful to think about hue and changing hue sort of directly, that it's useful to think about going from hue towards um, different amounts of saturation. And notice how, whether it's a single cone or a double cone, there's this sort of fall off effect. As you get towards white or towards black, you're less able to have a bunch of different hues, right? And so then at the tip where it's all white or all black, you can't tell the different hues apart. Um, so that intuition is well handled by this color space, whether we think of HSL or HSV. Now, let's actually dive into this a little more, just because it is going to be really important that you have a visceral sense of how saturation and hue work. So I really want to make sure everyone is understanding this. So these are very similar spaces where, again, fully saturated, really vibrant colors are around the outside of the hue wheel. And then in the hue HSV space, we think of going towards white as being the desaturated color. And then we kind of go from white down to gray and then to black. Um, or we could think of this double cone where desaturation is gray. So there's going to be this ambiguity. Sometimes when you think about a color ramp where you're going from fully saturated to unsaturated, sometimes it'll go to white, sometimes it'll go to gray. You might even see something that goes to some other, more neutralish color. Um, but for the big idea, we can think of these in a very similar way. So now let's understand, though, that luminance and saturation, these are not very separable channels. So they are both ordered, both luminance and saturation are ordered. But notice how in this case, right, we see, this value sort of looks a lot like we've been talking about luminance. And we can see that if we desaturate versus if we go towards dark, it can be pretty hard to tell the difference, right, if we're going in one direction along this matrix or the other. So we have to be really careful when we think about integral versus separable channels, as we'll get to in a few slides. These are not separable channels. We don't usually try to distinguish between them so much. So, even if we're doing quizzes, which we'll do in the sync class, understanding, did that change in luminance or in saturation? It's not crucial that you're able to distinguish those. We often use them kind of interchangeably. It is crucial that we understand, when are you around this color wheel changing the hue versus changing the saturation or the value. So let's come back then to, so this seems great. Does this color space meet all of our needs? And there's one huge problem, which is it sort of feels like it's a perceptual color space, but it's really a pseudo perceptual color space. That whether we pick lightness or value, neither one of these is true luminance. So here's actually an example in the upper right here, where we've taken the corners of that RGB color cube, and we can see, if you just sort of look at the top, it's obvious somehow that yellow is a heck of a lot brighter than blue, right? And in fact, we've even ordered these by their luminance. But in HLS, the L for lightness is not the same as luminance. So it's actually, these are all the same shade of gray. So if we're trying to do anything intelligent with any sort of ordered data, it's really, really tricky here because this RGB cube, they have such wildly different luminances for these different hues. So we see there's a way that, in fact, there's a relationship between hue and luminance, and it's a bit tricky. We can't, they're not fully separable because changes in hue also give us, as we see here, changes in luminance. So this is why these HSL and HSV color pickers are not perfect for visualization either. And we really do need to think about true luminance. Now I keep calling luminance L star. What's going on with that? Well, there's another one of these color spaces. So again, a color space is just a systematic way to think about color. And there's a very, very perceptual color space. Technically, it's called L star, A star, B star. And it actually corresponds with how our visual system and our brains actually deal with color. So what happens in your visual system, light comes in your eye, bounces around in your retina, and at some point hits the optic nerve and goes into your brain. What actually happens very early on in that process is that the light sensors in your eyes separate out the luminance channel, the black and white. That's actually how we see edges. And that's separated out from these sort of colorfulness channels. So let's look at this picture here. Here's a picture of apples in an orchard. And notice how all the edges are actually in the black and white luminance signal. If we separate out all that luminance information and all we're left with is a sort of colorfulness, the chroma, you really don't see very sharp edges at all. So what's really happening is that there are these three channels. There's a luminance channel, which is separated out by your visual system. And then there's these two other channels that sort of express information about colors. So there's the red-green and the blue-yellow. One of those is called A star and one of is called B star. And we'll get into in a later slide what some of the implications are for this in terms of color blindness. For now, I just want you to notice that luminance contrast is how you see edges. And what that means is luminance contrast is going to be completely crucial for reading text. And we'll get to that again in a later slide. So this true perceptual color space, L star, A star, B star, that's actually a really interesting color space to use for computation. So what's great about it is it's perceptually uniform. They've actually gone off and done a whole bunch of measurements about how the human eye responds to um, these sensory stimuli of colorful things, and they have come up with this measured space. It's usually called CIE lab, lab referring to this L star, A star, B star, and it's great for interpolating. If you want to interpolate colors and say, I want to take one space in CIE lab, that's going to look similar as to what the values are changing in your attributes. So this is a really good space for interpolation. The reason we don't just use this one all the time is it's incredibly hard to think about. this story that I've told you about how the optic nerve deals with color, it's true that that's what the perceptual system does, but if you're just sort of thinking about how to change colors, it's got this really weird three-dimensional shape. It's just not easy to think about. So the reason we like using luminance, saturation, and hue rather than luminance and this A star and this B star axis is it's just easier for humans to think about it. All right, so we've now talked through some different color spaces. We've really tried to get a sense of what luminance and hue and saturation are like. So now let's think about how to use these in a visualization context. So coming back to the idea of, well, is color categorical or ordered? The answer is it can be either one. It's both. Let's look at this example. Here on the top left, we see 4 years that are encoded with hue changes. So it feels very categorical, like, okay, we've got 4 different years. And here on the lower left, we've got something that's done with a saturation coding. So we've got this, light green, more vibrant green, even more, and then quite a dark green. And that really makes you feel like this data has an ordering. It really makes you notice the fact that these years are ordered as opposed to just these years are different from each other. So sometimes we'll make decisions. Do we want to emphasize the categorical nature of something, particularly temporal data, or do we want to emphasize the ordered nature of it? What we see here on the right is just to really emphasize, the fact that saturation really can feel a lot like a magnitude. Here we've got a corpus map on the left where we're color coding stuff, and on the right we've got a bar chart where we've got an attribute, which in this case is sales data. And we've redundantly encoded things with the length of the bars and with the saturation of the color. And we really can see that these align with each other very, very well. So we really can see that here color is being used in an ordered way because we are saturation coding. So we do want to think about color differently based on whether we want to encode categorical or ordered data. What are some of the things people get wrong with color? Well, one of the key things that almost everyone gets wrong their first time is they want to do more with categorical color than we can really get away with. So the problem is that even though in this legend, here we're actually looking at an example out of a biology paper with genomics, but this sin has been committed by many, many people in many, many contexts. So what have we got? On the left here are mouse chromosomes. This can sort of act as a legend. And we can tell the difference between even really subtle shades of green when they're right next to each other. So we can tell 5 from 6 and 6 from 7 and 7 from 8 because we're really good at relative comparisons when color is right next to each other, when it's contiguous. So we can tell apart these 7 different shades of green. We can tell apart, these blues from these purples. But what happens when we use these colors in scattered, non-contiguous regions that are small? So, and that's what we've done here. We're trying to encode where stuff that was on a mouse chromosome falls in the human genome. And what have we got? We've got tan, we've got, okay, green, brown, well, here's white. Oh, there's tan again. We saw that. Okay, looks like this red is kind of different than the brown. Wait, oh no, here's green again. We saw that. Okay, here's a blue. We didn't see that yet. Back to red. Okay, light blue. That's called cyan. That green again. Okay, here's a purple. Maybe that's new. Okay, maybe this green is different than that other green. So, weird green. Okay, wait, no, that's that same one we saw. Wait, no, we saw that. We saw that. So, okay, maybe orange. Maybe this is a little different. Um, Wait, have we seen that red before? Did we see that green? Is that green the same as this green? Is that green the same as that green? Okay, we just hit about 10. We're nowhere near like 21. And so we've got this real problem that we've run out of our ability to distinguish the colors. And so that running out is the fundamental problem with discriminable bins. We don't have as many ways to see these little tiny snatches of color that are all scattered about. So notice how even though we're really good at telling apart these two greens side by side, we're really bad at telling whether, is this green the same as that? Is this green the same as that green over there or that green over there? When they're scattered, it's hard. And so people always want to color code 20 different things with color, but in general, you can't. In general, a good rule of thumb is between 6 and 12 bins is quite safe. Remember that includes the background color. It might include like a default color. It needs to include any kind of a highlight color if you want to do linked highlighting. So people tend to want to do more than you can do with categorical color. So what are your alternatives? Remember, you have other channels. You don't only have to use color. Um, so you could, we already talked about this idea of having, multiple views where you're partitioning things by space. We could use other channels like orientation. Um, so all of the work doesn't have to be done by color, although people often want to do that. So the other thing we could do, which we'll talk about next week, is to deliberately aggregate. So what's happening now is your perceptual system is just sort of lumping all the greens together. And so the problem is that you can't really tell the difference between chromosome 7 and 9 very easily, even though it's pretty easy to tell the difference between chromosome 3 and 4. So what sometimes we might do is if we've got 20 things and we want to color code them, we might deliberately group them into just 5 or 6 groups. Then we could color code the groups. And since we made deliberate decisions about what group to group together, that's much safer than not making deliberate decisions and just letting your eye do that grouping in a less thoughtful way. So here's another example. This should look familiar to you. We've seen this before. Notice how they're actually doing something pretty similar. Like this, you know, retinitis pigmentosa, is that the same color as the deafness color? What about leukemia? Getting pretty hard to tell, like hypertension versus blood type. These are both sort of, maroony. Um, so we really have, I can definitely tell obesity apart from deafness because it's sort of orange versus blue. But when we look up here on this legend, then again, colors that seem really distinguishable when they're right next to each other are really hard to tell apart when we've got these little scattered patches of color. So this is an example of trying to fit too many things into a color coding. So be very careful about the number of bins you try to use with categorical color. Now, there's a similar issue with ordered color. How many bins can we tell apart when it's ordered? And again, if you just look at the legend, it's a little misleading. So we saw this before when we were looking at choropleth maps, when we were thinking about spatial data. So don't focus on the legend up here, focus on the map itself. Really easy to tell apart two classes, light pink versus, dark maroon. 3 is not a problem. We can get sort of, light and medium and dark. Even with 4, there's, light, medium, darker, darkest. But, once we start getting even to just 5 classes, it's not necessarily easy to tell apart, is this the very lightest color? Is there any difference between, like, say, Pennsylvania and what is that one? New Mexico? Um, So things get tricky. And by the time we get to like 8 classes, again, we can see differences on the legend. But once we start saying, okay, Maine, is that the same color as Colorado? Is Florida the same color as Arizona? These really subtle distinctions between like bins 6 and 7, they're almost impossible to see on the map. So we're not really succeeding in reading off the information about this large number of ordered classes from what we're able to actually notice with these gradations of, in this case, you can think of it as, whether it's luminance or saturation coding, we're definitely seeing something that's ordered, but we're not able to distinguish all those bins. So 2 or 3 seems totally safe. Even 4 is maybe okay, but things start getting pretty dicey once we're in like 5, 6, 7, 8. So it seems like we've got some pretty strong limits for both ordered color and categorical color if we want to see individual scattered pieces and understand when they're the same color and when they're different colors. The other big thing people get wrong is rainbows. So a lot of people have chosen to use rainbows for ordered data, in part because it's the defaults on a lot of software, sadly enough, and in part because they've got these intuitions that don't really pan out. They have this idea that since rainbows are a physics phenomenon, it's natural that we must be able to see the ordering of the rainbow implicitly. But we already talked about how we don't. We could consult a legend, we could memorize the order of rainbows, right? Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. But I had to memorize that many, many years ago. That was not perceptual. Um, and so there's this perceptual lack of ordering problem. But even worse, they're not even linear. I actually have two equally sized red boxes here. I know they're equal size because I made one and I cloned it and moved it. Notice how in the one on the left, I can see red, orange, yellow. I clearly have this gradation, maybe even a little bit of green, but at least I can see there's red and there's orange and there's yellow. And this box of the same size over here on the right, it's just all green. Right? I can't tell the difference between these greens. So the problem is that a step in the space of the attribute value might be distinguishable in the color space, and it might be not, just according to where we are along on that rainbow. And so that nonlinearity is a real problem. Um, so what's going on? Here's a couple examples of using a rainbow color map. This one here on the left might be reasonable in certain contexts, right? One thing we see is we see a lot of fine-grained structure here. We're able to see like the red region, red and orange versus like cyan. So we can talk about, the red versus the yellow. Um, and so there's some contexts where we might want to see that. We really do see these, 3 or 4 regions where there's red. Um, Down here, it's pretty hard to see what's going on with this. It's not obvious what this shape is. There's a sort of big yellow blob. Um, but what if what we want to see is not fine-grained structure, but large-scale structure? Well, here's an alternative to the rainbow. Notice how we have purple on one side, yellow on the other, and they sort of meet in the middle and they desaturate towards gray. So notice how in this view, we're seeing, the same sort of fluid flow, sort of turbulent flow thing as on the left. Um, we aren't really emphasizing these little regions where it's red versus yellow, and that allows us to really see the large scale structure much more easily. We can see sort of these shock waves coming out from the yellow region into the purple. So there's a way we're really much more able to focus on the large scale structure and see that more clearly because we're not sidetracked by these things that might actually just be artifacts. It looks like there's a really sharp boundary here. But maybe, in fact, that boundary is not conceptually very sharp at all. It really is more of a continuum. So depending on whether you want to emphasize the continuity of the, continuous data versus these discrete changes, we can think hard about whether we want to have many colors or just a few colors where we interpolate between them. And let's take a look at what this data set really is. Was not obvious that that was the coast of Florida because here that crucial 0 point, this is actually showing sea level, was in a very difficult to distinguish part of the rainbow. Whereas notice how what we've done here, we've picked a couple of different hues. We have a really sharp segmented line at something that was meaningful, right, sea level, and then it goes from greens towards white for altitude, and then from light blue towards dark for undersea depths. So, and we're really able to see that structure well because of a carefully chosen color map. So if we want to have it both ways, if we want to have a lot, both fine-grained structure and also show ordering, what can we do? We can be careful about how we combine luminance and hues. We can have multiple hues, but we want to make sure that we put them in order of luminance because the rainbow is not in order of luminance. We've got sort of dark red and then it goes quite bright for the yellow and then a little bit, still a little bit dark. And then, but then notice how it gets dark again. So it starts dark and gets bright and goes dark again. That's not monotonically increasing. We want the lumens to be monotonically increasing. So let's look at an example of a color map that's actually designed to do exactly this. Notice how here's a few alternatives, and down in the bottom here are these color maps, Viridis and Magma, and they were designed to have the luminance go from in this case, very bright to very dark, even as we have multiple hues along the way. So yellow and green and blue and purple, those are ordered by their luminance. And with magma, right, it's a different ordering. We've gone with, yellow and orange and red and pink and purple, and then dark black. And that gives us a really strong perceptual ordering because of the luminance change, even as we also have perceivable and nameable hues. So here's a few examples of some uses of these two color maps. Notice how they are perceptually nicely linear. They're this perceptual uniform where going a step in the color ramp is sort of equal size perceptually as the size in the data. So we don't have that problem with rainbows of the perceptual nonlinearity. We'll be talking more about colorblind safe. I'll just note for now that these are designed to be colorblind safe. And these are built in these days to all the major tools, including D3, not to mention R and Python. So that was an example of a color map that has multiple hues, but also monotonically increasing luminance and is perceptually uniform. So that's an alternative to the rainbow. Um, I want to point out that there's situations in which rainbows are actually good, not bad. If you're trying to show categorical data, then we actually really like rainbows because they are highly saturated. And when you have small little scattered regions of color, we really want to have something highly saturated so we can see it. So this, because the smaller something is, the harder it is to see color, and the more we need to have saturated colors to be visible. So if you've got categorical data then and you want to segment it rather than show something as ordered, then in fact rainbows can be perfectly good. So like almost every answer in visualization, is something good or bad? It depends. It depends on what you are trying to achieve, what the task is, are you showing, and what the data is. Is it ordered or is it categorical? So let's talk more explicitly about interaction. Remember when we talked about channels, we talked about, are they integral or separable? Are they able to show different information in full, or do they step on each other's toes? Do they sort of merge together? So hopefully you've already noticed there is not a lot of separability with color. There's a lot of integral behavior. So the channel of size really affects the salience, the noticeability of the color. So you need highly saturated colors to be visible in small regions. Conversely, if you've got really large regions, then highly saturated color kind of blows out your eyes. You want unsaturated or desaturated colors. So like we see here in the top, where you have large regions, it's nice to have those be desaturated. Now, the other thing, as we alluded to already, is saturation and luminance are not separable from each other, and they are not separable from transparency. So I'm actually showing the ColorBrewer tool here, where we've got fully saturated colors, but notice how the transparency slider is moved over. So we've got a transparent layer in front, and we basically can't tell this apart from unsaturated colors just used to directly color code. So transparency is not separable from saturation or luminance. So we can sort of pick one of these three if we want to encode data directly. Often people use transparency to create layers, as we talked about with layering. So keep in mind that if you're using transparency for layering, you're not going to be able to visually encode anything with saturation and luminance. So in terms of the number of bins, we sort of already walked through a bit that, 2 bins is definitely safe. Maybe you can hit 3 or 4 bins. But if there's small separated regions, you don't want to go beyond that. But of course, if it's contiguous regions, like a sort of continuous phenomenon, then you can see fine-grained differences. We'll talk more about this tool that was used to create these color palettes called ColorBrewer in a later slide. So let's talk about color palettes. So first of all, let's talk about whether you just got one attribute, univariate color palettes. So we've talked about this idea that you could have categorical color. And then what we're doing is we're typically aiming for the maximum distinguishability. That often means highly saturated. Sometimes, especially if you look at the cartographic literature, you'll see these called qualitative maps or nominal. We're just going to continue using categorical because that's the language we're using here in this class. And here's several examples of them, right? Both desaturated and highly saturated. And so we're really going for maximum distinguishability. Now, what else could we do? If we have ordered data, then we're often doing something with saturation or luminance, and we really want to distinguish between sequential and diverging, Remember back when we talked about data types, we emphasized that you might go from a min to a max, or you might have a 0 point and go up and go down from there. And so color palettes are really the prime example of where we see this used in visual encoding. So here's a number of different color palettes, both diverging and sequential. And hopefully you can see the structure, min to max versus 0 point up and down. That 0 could be, a white, it could be a gray, it could be a yellow. We want it to be some sort of neutral feeling color. And like the color maps we saw with that gray yellow one, we often want to pick two hues that are fully saturated on the endpoints and then interpolate to some neutral midpoint color. So with sequential, we're typically then going from some sort of min to max. We often want, whether it's the luminance or the saturation, we want that to just smoothly vary from a low value to a high value. And that's what we're seeing here. So, here's a number of different color maps. Notice how, some of these really are trying to have it both ways. Like we already saw the viridis, where we are varying both the hue and the luminance. With others, we're doing something maybe a little bit more subtle. So we can, of course, combine these where we change both hue and luminance or saturation to make more complex palettes. Sometimes we do want to emphasize that the data repeats, that there is some sort of cyclic phenomenon. That's one of the few situations where we do actually do something a bit more rainbowy, or at least highly saturated. So we can have these different multi-hue ones. There are some of these, again, built into D3 if you want to really emphasize, are there repeating patterns? But make sure to be careful that you do deliberately want to emphasize the cyclic nature of the data with these. Um, and we'll talk more about some approaches to this later on. Okay, so what else could you do? You could have a bivariate color map, and that's where you're trying to encode two different attributes with color. And so this is something we have to be very careful of. The best case that works pretty well is if you've got a binary thing in one of the directions, like just two saturation values, low and high, and then you vary something like hue categorically. So people are really able to understand this. For example, here's one of the schemes built into D3, the paired scheme. If you look at the D3 documentation, you're going to see it shown like this. To sort of think about it as a bivariate color map, it makes more sense to sort of chop that picture up and show all the low saturation and then the high saturation with the pairs sort of next to each other in 2 dimensions. So we really can think of this as a two-way color map where you could encode two different attributes. So one with the saturation value and one with the categorical hue value, and then you can see those pairs. Now, it's possible, but very tricky to really go further than binary, to have multiple steps in each of those two directions. It can be very difficult for people to interpret it. So people often use this sort of aspirationally, hoping that it's easy to understand, where in fact often it's not, even if people go back and look at the legend. So be careful with these complex bivariate maps that don't just have a binary value in one of the directions, but 3 or even more. These can be quite hard to interpret. And so notice how just in this little layout of what we can do, we can think about, are they diverging or sequential? Binary is sort of a special case where you just have two instead of many. And so you could have, binary to categorical, you could have categorical to sequential, sequential to sequential, diverging to diverging, diverging to sequential. These are all possible, but these complex ones down here can be quite tricky to use, so be careful. So to remind you, what kinds of palettes are there? Well, there is segmented, meaning chopped up into little, visibly different blocks, versus continuous, where you've got a smooth ramp. So we can have diverging versus sequential, or, categorical. And we can think about, do you have a single hue for sequential? If you've got two hues with a neutral in the middle, then that's really diverging. And you could have sequential multi-hue, as we talked about with things like viridis and magma. And then finally, we could have something that's cyclic. So when you think about color maps, think about these questions. Is it segmented or continuous? Is it diverging or sequential or cyclic? Is it just one hue or two hues or many? Is it perceptually linear? Is it luminance ordered? And we'll get to this question of colorblind safe in a moment. So color blindness, or it's more technically correct, color deficiency. So let's go back to that perceptual L star, A star, B star color space and think about that. So we've already seen a lot about the use of luminance. And of course, remember that luminance is crucial for reading text, any kind of edge detection. But what's going on with these other two channels, right? We talked about this chroma channel that, red to green, you're able to see variation, and yellow to blue. We're not going to get too deep into the eye's anatomy. Cool subject. We just don't have time in this class. But I do want you to know one thing, which is what can go wrong. One of these axes can be much less able to actually be sensed in certain people that have a genetic mutation, and it's sex-linked. So it's much more common in men than in women. Roughly 8% of men are red-green color deficient in some way. And so what's happened is, think of this axis as just sort of collapsing. It's either gone completely or it's much shorter than it normally would be. So variations between red and green we're not able to actually see. It is possible, but extremely rare, to have a genetic mutation that affects the blue-yellow axis, so we don't typically worry about that in a viz context. We worry much more about the red-green because that's the more commonly affected axis by a common mutation. So what happens with red-green colorblind? Well, things that are really easy to tell apart for people with normal vision, in fact, can be really hard to tell apart. So there's big words for these. Basically, one means there's these sort of two flavors of red-green, one where you're weak in the green, one where you're weak in the red, deuteranope and protanope. And then the much less common one, the tritanope, is where you're weak in the blue. So notice how that doesn't mean you can't see any color at all. This is using a colorblindness simulator where we are able to see some things apart because we don't just have hue variation. We have other variation as well. So it's not such a huge problem to see these flowers apart. But notice what happens in this heat map where we've got like the red and the green. It's very hard to understand what's going on when you're red-green colorblind in these kind of when you're just directly encoding with the red and the green. You can tell the luminance differences, but you're not able to tell apart the hue. So, well, what are some alternatives? If you run a colorblindness simulator and you discover, wait, I can't tell apart some crucial part of my color coding, what are some alternatives? Well, one thing is, remember, you don't just have the hue channel, you have other channels. So you could vary one of the other channels redundantly with red and green, because sometimes there's domain meanings, like finance is always using red and green, and that meaning can be extremely useful, and you don't want to give up that meaning for the people with normal vision. So for example, you could redundantly encode. Notice how we've got a completely distinguishable color map here. It is red and green, and yellow in between. But because they've also carefully changed the luminance, we've got that the red is a lower luminance compared to the bright green, with yellow deliberately in between. So we can still tell these apart. We don't have that sort of pop out of the red versus the green for the colorblind folks, but it is distinguishable. Here's another example. We don't just say, let's have a red dot and a green dot. We can say, let's actually have the red be an X, so we can tell apart the shape as well as the color. So we could change the shape, we could vary the luminance, we could even do all three. So remember that you can avoid simply having hue be the only distinguishable thing. So really, the way you might want to think about this is that color deficiency or color blindness reduces the color to from a sort of three-dimensional space to really more of a two-dimensional space for those people. So you can think carefully about, does it matter for the task that you're doing? Are you going to worry about that for the audience? Color is very, very powerful. Categorical color coding is a really, really strong channel for showing you categories. So you don't necessarily want to give up on it, but do be aware that some people will not be able to distinguish all of that. So just as a rule of thumb, in general, don't, unless you have a very good reason, don't pick a red-green color map. Something like a blue-orange color map is much safer as a default. So keep that in mind. Particularly, this is going to come up with your final projects. Think about color deficiency. Think about whether you need to design for it. And if you're using red and green, have you varied the luminance? Could you pick other colors if there's no domain-specific meanings that are crucial? So think carefully about that. Be prepared to justify your choice of red and green. Okay, so a few more things to think about with color. Unfortunately, color doesn't just exist in a vacuum all by itself, like we've talked about it so far. Actually, what matters is what other colors are next to it. So the interaction with the background, notice how we have this terrible, hard to read thing here, right? That what we need is we need luminance contrast between the foreground and the background. Otherwise, things are incredibly hard to read. So we can read the dark blue against the green pretty well, but like, one shade of blue against the other, almost impossible. Like dark blue against black, almost impossible. So notice how here's just a few of these color palettes where we notice that, when the background is white, it's great to see the black text. And when the background is black, of course, we can't see the black text at all. And, different versions. Yellow, very hard to see against white. Obviously, uh, red on blue, not a very pleasant color at all. So the thing you want to remember is you're seeing edges because of luminance contrast. And so if you don't have sufficient luminance contrast, it's going to be really hard to read text. Again, think of this in your final projects. Be aware of these issues. Be aware that you can't really see yellow against white very well. So, be aware that you're going to have to think carefully about what colors you're using. And if you have a black background versus a white background, you're going to have to make different choices. So think carefully about that. So here's an example, right? With a black background, we can have a really bright yellow. We can have a high luminance yellow, and it's very visible. It's popping out because that's a really big luminance contrast. Notice how if we have a white background, we can still use yellow, but we should be careful about what yellow. That same yellow we used before wouldn't work well at all. We've actually gone down to a medium luminance since we've got a high luminance background, because white is the highest luminance you can get. So let's just take a look at these side by side. Notice how, you might think, oh, they're both yellow, but these are actually quite different shades of yellow we can see when they're side by side. And seeing that pale yellow against the white would be much more difficult. Keep in mind sometimes also you might want to make sure to outline things if you need to, if you've got enough pixels to do that. That can be a way to make sure that people are using some sort of sharp edge rather than just a hue difference to notice shapes. So here's what might seem like a silly question. I have two different, obviously these are little paint swatches, and one's in shadow and one's in the bright light. I'm gonna ask you a dumb question, which is, okay, so here's the black one here and here's the white one there. Are these the same color? And the obvious answer is, of course, they're not the same color. Look, it's the same manufactured color swatch. Obviously, that's the black one and that's the white one. And then if I go and I just put a mask on this picture, wait, what just happened here? This is actually the same color. And so, well, what does it mean to be the same color? There's this issue that color constancy, our ability to sense color is completely dependent on illumination. Our brains are automatically, we don't actually care that technically these are the same color. What we care about is that one was in shadow and one was in bright light. And so our eyes are sort of, those of you who know about cameras and white balancing, our eyes are automatically white balancing so that we can sort of get the sense that this pink and that pink are supposed to be the same color, even though the lighting conditions are different. This is fantastic for navigating everyday life, right? Not falling over when there's a shadow. This is really good, understanding that this purple is the same in sunlight as in artificial light. Um, It's really bad for visualization where we're color coding things because we create these situations that invoke the same circuitry in our brains that are used to try to automatically figure out what color things are. It can really be a problem for the color coding. So this part where our ability to perceive color depends a lot on the surrounding color really adds complexity to our ability to color code. So it's not just, of course, for colors, it's also for things like luminance and black and white. So here you see we've got a dark strip on the top and a light strip on the bottom, but whether we perceive it as dark or light just depends completely on what the background is. So, here, notice how, here it seems quite light, here it seems quite dark, but it's actually the same color in both cases. Ditto here on top. This seems light, this seems dark. It's actually the same color if we were to mask it out and just look at that. So we see these really massive contrast effects. Those of you who followed, there was controversy a few years ago about the dress, whether it's black and blue or white and gold. When I was making my slides, I started in the full sunlight and I'm like, obviously it's black and blue. And then later I looked at it at night under artificial light and I'm like, oh, it's just white and gold. Wait, that just flipped on me. Um, so whether you see it as black and blue or white or gold depends on what your eyes are thinking of as the illumination in the scene, whether you are seeing it as something that's brightly lit or as something that's more in shadow. Um, if you want to dive in more, here's a few links to go. Basically, this was an example where instead of just being something taught in a visualization class, suddenly the entire internet melted down about color constancy and color contrast, which was fun for those of us who like vision science. So this phenomenon does make life difficult when encoding. Even more, there's all kinds of phenomena that have specific names in the perception literature. For example, the Bezold effect is just the name for the effect of that the outline, right, whether you outline a color in white or black, really matters immensely on how we perceive that color. These are a whole bunch of examples from Maureen Stone, great slide deck. So when it comes down to it, if we just say, I give you this precise value, maybe in the most, heavily measured space we have, CIE lab, if I just give you this number, what color is it? The answer is it depends. It depends on, what other colors are near it. It depends on, how bright of the room is that we're looking at it in. It depends on all kinds of effects like what angle we're viewing from. So there's a lot of phenomena that actually affect color appearance. So we've only scratched the surface of it in this slide deck. We've gotten little teeny tip of the iceberg. There is so much more to color. But we are only spending 1 week on it, so this is what we get. But just be aware that there are complexities. For example, naming. Does it matter what name a color has? So there was this joke that went around again on the internet a while ago about gendered perception of color and how some people are noticing many more shades versus others and how gendered that was. One of my favorite comics, XKCD, actually was like, let's survey people. Let's actually find out. And in addition to noticing there were some gender differences, although far less than the caricature, what they have is this fantastic database of what a bunch of, they got thousands of people to take this survey of, they showed them a color and they asked them for the name. And so we have this database of color nameability. And so, it turns out that being able to name colors, right, being able to say red versus green or blue, as opposed to like sort of light gray, versus not quite so light green, um, it actually does help to communicate about a visualization, even being able to, remember and think about these regions differently. So it's even possible to integrate color naming into color models. So in addition to how things look, you can also take into account the nameability of colors. So that's just another part of the complex world that is color. Um, and do remember that color is only one part of the visual system. It doesn't, it's very separable from position, from shape, although there is some linkage with size, as we talked about, from motion. So it is only one piece of the visual channel space. Remember that. Okay, so what about practically, what tools are out there to help you deal with color now that you sort of understand some of these theoretical foundations? Um, so we've already seen an example from ColorBrewer. This is a great tool if what you're trying to do is come up with some categorical color maps. There is a little bit of customization possible. Basically, you pick the number of channels you want, and there are a few options like whether you want it to be, print well in black and white or be colorblind safe. And then it will actually generate some of these color palettes for you. So colorbrewer2.org. We are going to be playing around with that some later this week. And again, here's another example of how the size affects the salience. We want these really saturated colors for like the roads going over these less saturated, desaturated background regions. Um, and notice how it's quite visually salient to the point of jumping out at us when we have these huge regions that are highly saturated. We like it for small regions, but try to avoid it for the larger regions. So ColorBrewer is a great tool for categorical color particularly. You'll notice how if you try to tell it to pick a 20 level color map, it's simply not going to allow you to. So it's got a certain amount of color knowledge from cartography built into it. I already talked about this idea of colorblind simulators. A handy one is the Coblis one, which lets you just upload a picture of your choice and then see what it looks like. So you could and should, when it's relevant for your projects, check it with a colorblind simulator to make sure that if you think you've got a color palette that is colorblind safe, check if it actually is, and think about when you will care about that. There are many color pickers out there. Most of them are used for general design purposes, not particularly for visualization. The Adobe Color Picker is one of many that does allow you to try to find some sort of colors according to graphic design style color theories of finding colors that might go well with each other in a palette. Um, there's some really specialized for visualization tools. One that came out a few years ago, Colorgorical, very highly customized, huge amounts of power. You could pick things like the number of colors and worrying about perceptual distance. And remember how we talked about name models. It can take nameability into account. You can give it different ranges of hue and lightness. So if you really want to go to town with categorical data, this is one possible tool to use. Okay, so what you're going to care about the most, of course, is color management in D3. So a few of the main sections, D3 color is really about converting back and forth between color spaces like the ones we've talked about. We talked about RGB and, luminance, saturation, and hue, and HSV and HSL, and there's a number of other color spaces. So it's a very low level component. Of course, D3 scale will let you customize if what you want to do is to grab some colors, maybe that you generated with one of these tools we just talked about, then you could actually use D3 scale to make your own. You could use either sequential or ordinal. So it's possible to do that. But for almost all of you, what you're going to want to use is the D3 scale chromatic. This implements a lot of the base stuff you might want. It's got a number of good color schemes and scales. It's really quite high level, ready to be used. So for most of you, you will be wanting to use D3 scale chromatic in your final project. Okay, and a few credits for this one. And now we will wrap up.